We're calculating capacitance for different geometries. We already saw at some point that the capacitance, so let me just tell you this, capacitance C is equal to Q over delta V. So this allows us to find the capacitance of different shapes if we know the potential difference. So for example, we can find the capacitance for a coaxial wire by first getting delta V. So let's do it this way. Let's say capacitance for coaxial wire. So let's consider a coaxial cable shown below. We can say that the charge on the inner wire is Q, and charge on the outer skin, or I guess you can call it skin if you want skin, is minus Q. So let's say we have this arrangement. So this is Q and this is minus Q. So this is a coaxial wire. We can say that, so this is Q. So the inner radius is that, and that's outer radius. So inner radius is A, outer radius is B. And we are saying that what is the capacitance between the two, what is the capacitance between the coaxial cable? So what is the capacitance at some point R between the conductors in the coaxial cable? So we can solve this. So if you look at it from the top, you will see that this is A, and then this will be B. So this is the outer sheet, which is minus Q, and the inner one is Q. And so we can take a certain point in here at a distance R. So we are interested in the the capacitance in between those two plates at the distance R. We know that by definition, capacitance is Q over delta V, where we can say the potential difference delta V is VB minus VA, and VB minus VA is equal to minus the integral from A to B of E dot ds, where E is the electric field between the plates. So this is the electric field going from the inner conductor to the surface. So we already know the electric field for a straight wire at some distance R from the wire. We did this multiple times. So we know the electric field is equal to 2K lambda over R, where lambda is charge density. So this is the electric field that we found at some point when we did this example. So it's 2K lambda over R, and we already know lambda is charge density and K is 1 over 4 pi epsilon naught. So let's use that. So we can plug that in there. Since the electric field is radial and parallel to the direction, we can say that VB minus VA is integral from A to B, and E is, so we have E, R, B, R. So the electric field is in the radial direction. So it's minus the integral from A to B of 2K lambda over R, dr. So that will give you VB minus VA minus 2K lambda A to B 1 over R dr. So we can solve that. What is the integral of 1 over R dr? So that's a natural log of R going from A to B. So how do you complete this? So VB minus VA can be written as 2K lambda natural log of B over A, because natural log of B minus natural log of A is just natural log of B over A. And so I think that is how we finish it.
Okay, you're going to factor out the 2K.
Yes, the 2K is not variable, so that can stay out. And we can say that if the coaxial cable has length L, then we can say that the charge density lambda is equal to Q over L. Therefore, we can replace lambda by Q over L if we want. So we can say VB minus VA is equal to minus 2q 2kq over L natural log of V over A. So that's the potential difference between the plates, and so we can use that. And so from here we can say that capacitance C is equal to Q over delta V. And so we're taking the magnitude. Using the magnitude delta V, we have C equals Q over delta V, which is 2kq natural log of V over A, and then the L at the bottom comes up here. So we can take the Q's out, and we shall have L divided by 2k natural log of V over A. So this is the capacitance of a coaxial cable of length L. Now let's look at energy. So I'll wait for you a few moments to finish writing. Okay, so let's go to 29.6, energy stored in a capacitor. In the previous exercise we just did, we used the magnitude of delta V, because remember that the capacitance is a scalar quantity, so the direction, there is no direction. So the negative sign is not a direction indicator. It just indicates that the potential difference is decreasing or it's dropping. So it's not an indication of direction. So when we find capacitance, we're using the magnitude of delta V, not the actual delta V, which is negative of that quantity. So we use the magnitude. So that gives us a capacitance. So let's look at the energy stored in the capacitor. So I already mentioned at some point that capacitors store charge, and within that charge, of course, is the energy. So when we charge a capacitor, basically what you are doing is forcing charges onto it. So you have to, so basically what you're doing is putting energy on the capacitor. So we can say by charging a capacitor, we are storing energy in the capacitor. So we know that we have the capacitor plates like that. We are putting charge Q on it. So let's say that's minus Q, that's positive Q. So I'll put the positive terminal here. So the capacitance is C, which is equal to charge over potential difference delta V. And we can say that the work done to charge this capacitor plate is given by the charge Q times the potential difference delta V. Work done is charge times potential difference, where delta V is equal to Q over C. So we can say that the work done is equal to the integral of what then is charge times potential difference. So this is delta Q dQ. So the element of work dW is equal to dQ delta V. So it's going to be dQ times delta V, where delta V is Q over C dQ. So the work done is equal to Q squared over 2C. Assuming the initial work is 0 and the final work is W, then it's just Q over that. So we can say Q squared over C, charging from an initial point of 0 to, let's call it Q, so 0 Q. So we shall have Q squared over 2C as the work done. So the total charge is here is uppercase Q, not lowercase q. Make that change. Uppercase Q is our total charge. So make that correction. Uppercase Q. So I'm integrating from 0 to uppercase Q. So this is the work done or the energy stored on the capacitor. We can also change that a little bit. So as an exercise, so show that the energy stored on a capacitor plate can be written as 1/2 C delta V squared. That's the exercise for you to try. So what you need to do is to use the definitions that we have and the work formula and convert or change that into the new formula for energy, 1/2 C delta V squared. Okay. So how many finished this? Okay, a few people. All right, very good. Almost, okay.
Half C.
All right, so what you need to do is to know that C is equal to Q over delta V, or you can say Q is equal to C delta V. Then you use your formula W equals Q squared over 2C, and just replace Q by C delta V. So once you replace Q by C delta V, that should give you the result. So Q is C delta V squared divided by 2C. So it will be 1 over 2C, and you have C squared delta V squared. So you can cancel one of those. That should give you half C delta V squared. Okay. All right. Any questions on that? Okay. Let's finish up with dielectrics 29.7. I'll put a new page up. Dielectrics. So a dielectric typically would be an insulating material. So insulating material that is inserted between the plates of a capacitor. And typically what that will do is to increase the capacitance. So a dielectric typically increases the capacitance of the capacitor. So examples of dielectrics, you can have air. So if you have a parallel plate capacitor, which is just in air, then the dielectric is air. You can have a parallel plate capacitor with paper in between the plates. Paper is a dielectric, or you can have plastic or wax or any type of insulating material, ceramic perhaps. Those are all dielectric materials, so they will increase the capacitance of the capacitor. So in your textbook, table 29.1 has several dielectrics. So let me point you to that. Okay. So table 29.1 has several dielectric materials. A dielectric is specified as having a dielectric constant. The dielectric constant is K. And in the textbook, it's actually kappa, but since I can't really write the Greek letter kappa to make it look different from a K, that's why I'm calling it a K. So it's a dielectric constant is K. So for example, air and vacuum have dielectric constant of 1. And then if you have plastic like polystyrene, that's 2.6. Paper is 3.7. There is water, which is 80, and so on. So there are different elements, different compounds there that have different dielectric constants. Okay. So let's look at what effect this would have on a capacitor. Okay, so we'll do it. So let's say that suppose we have a parallel plate capacitor of capacitance C naught and potential difference delta V naught. Okay, so we're saying that capacitance is charged with potential difference delta V naught. It has a capacitance C naught, and the total charge is Q naught. So we have a capacitance already, the capacitor already charged to Q naught. Potential difference is delta V naught, and it has a capacitance C naught. So we can put a voltmeter across this, and we know what the potential difference is. So if you put a voltmeter across, it tells you potential difference is V naught. Okay, so let's see. This is the positive and this is the negative plate. We can now, let's say with the voltmeter still across it, if we put a dielectric material in here, okay, that we know the capacitance is still C naught. If you put a dielectric material there, you will see that the voltage will now change to delta V. The voltage will now change to delta V. The charge on the plate does not change, so the charge is still Q naught. The voltage is now different because it's now a dielectric between the plates. So we see that, so dielectric of constant K is placed between the plates. The voltage changes to delta V. And we can say that the charge on the plate is still the same. The charge on the plate is still Q naught. So the capacitance is now given by C equals Q naught over delta V. So initially we had capacitance C naught. Let's see. We had a capacitance C naught. So the capacitance C is now given by Q naught over delta V. So this is after dielectric. So originally what we had was C naught is equal to Q naught over delta V naught. Okay, so after the dielectric, the C is equal to Q naught over delta V, where delta V is equal to delta V naught over K, since the voltage decreases. So putting the dielectric in the plates will decrease the voltage. So the original voltage is delta V naught. Delta V is delta V naught over K. So we can say C is equal to Q naught over delta V naught divided by K, which brings the K up. So C can now be written as C naught, where C naught is the original voltage. Original capacitance. So this tells us that the capacitance is increased by putting a dielectric between the plates. So the dielectric will increase the capacitance by a multiple of the dielectric constant K. So what this means is that if you are working with capacitors, if you wanted to increase the capacitance, you could use any of this. You could use, for example, Teflon, plastic, paper, or anything to increase the capacity. So if you have parallel plate capacitors, 50 microfarads, you can increase it by putting paper between the plates. So if you put paper, the dielectric constant is 3.7, so it will be 3.7 times 50. So you multiply your capacitance from 50 to 185 microfarads just by putting paper between the plates. Okay.